Greetings again, everyone. Welcome to my channel, Professor underscore 101. In this lesson, I will be talking about trigonometry and the whole concept behind TOA. Now, if you look on the board, we will see that we have a circle and also a scale that we're actually going by. So this is referred to as a unit circle, where the radius from this point here, which is the origin, to this point on the circle is actually 1 unit. So in this lesson, we'll be talking about how right angle triangles actually are used to solve various equations using the concept of TOA. We'll be demonstrating all of that using the unit circle. Now, just some little few pointers up to know about the unit circle. As I said, from the point origin here to this point on the circle is actually 1 unit. The next thing to note is that all of these, the other values are in 0 points. So this is 0 0.1, 0 0.2, 0.3, 0.4, all the way up till it reaches to 1. We can also see that if we look here as well, that these values are my negative values, and these values here are also the negative values. So these are my negative y-axis values, and these values are my negative values for the x-axis, right? These are the positive for the x, and these are the positive for the y. So that's some basic things to note. Also, just remember that this point of the origin is 0, 0. So where this point right here is there, this point, the x is going to be at 0 right here, whereas the y-axis, this coordinate of this point right here, is going to be 1. We know that when we're actually doing coordinates, we do x first and then we do y. So right here at this point, the x-axis is directly in line with the origin, and then we know that right here this point is exactly mapping towards the one on the y-axis, right? So that's how we actually read them. So the same is true for here. The x right here is directly in line with the -1 right here, and the y-axis would actually be right here at 0 at the origin. All right, so those are just some few pointers to note. Now you will see the unit circle where y squared plus x squared equals 1. We'll actually be, even to explain, even that we'll be doing a little demonstration how that actually came about, this equation actually came about. Alright, so here we also have our definitions of our equation for sine theta, opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. Now, with that being said, the first thing that I'll be doing is that I'm going to take my little protractor right here, and I'm actually going to make a point on my circle, or right here from the origin. I'm going to take my protractor, and I am going to actually do 40 degrees here. All right, there. The other thing I should have done as well is just to highlight this point right here. This point on the circle right here is where I'm actually drawing the line from. We want to find the coordinates of that line. So we're going to look at the coordinates of that line. We do x first, and then we do y. So right here at x, we see 0.7 something, right? So that's going to be, it might be 0.74, 0. Something about that. So 0.74, for example. That's what we're actually doing right here, right? So we're just mapping something right here. And this is literally going to point to something very, very interesting as I am doing this. Right? So here now, drawing another dotted line here. Trying to get the road out to be straight as possible. Alright, you can look at it yourself. I mean, that really looks straight, right? So, well, to me, it looks straight. Hopefully, it looks the same, right? Now, you can actually take a graph paper, right? You can take a graph paper like this. I was actually doing this, but I realized that I didn't take note careful of my axis, of my labeling, and I realized that the points actually, the points were actually too short. So I wasn't mindful. I thought that I would have gotten the entire 1. Right here has to be 1. So here is going to be 1 because it's a unit circle and the radius must be 1. So right here should be 1. Right, so you can actually draw a circle like this and actually draw your angle here, and you can actually maybe even pause this video and try to follow along. All right, so let us look at what we have right here. Now right here is theta. So this part right here represents theta. So this is theta. Okay, so that is theta. Now understand carefully now is that when we look at here, right here, remember now that when it comes on to a scale, the vertical line, if we were doing like rise over run, the rise would actually tell us what's on the y-axis. So right here would be like my rise. So right here is my y-axis. And down here is my x-axis. But I didn't really put anything down here. I actually drew some lines right here, right, to actually map where this point on the y-axis is actually connected to. But if we were to really use that line, it would actually fall straight in line with this vertical axis just the same, right? So it's as if this now would actually be right here just the same, right? And here now would actually be pointing to here. So that's how I want you to understand what's going on here, right? So though this line is the y-axis, this one would represent the x-axis, but I didn't want to interrupt with my red line right here, right? So look carefully now. We see right here that the y-axis, the value of the y-axis actually measures, as I said before, something about 0.74, just using what I have, using my eyeballs to maybe decide what is the value of y-axis. So it's there about that. And oh sorry, my x-axis rather, not my y-axis, my x-axis. So my x-axis is 0.74. So this is my x-axis and the value is about right there, right here, somewhere there. So, but my y-axis is actually right here. So this is my y-axis. This line, if we were to put it here, it maps straight in line with this right here, about 0.6 something. It looks like maybe 676, something about that. 6.5, 0.667, thereabouts, right? So those are the all estimations, right? If you were using a graph paper, I'm sure you'd have gotten that more accurately than I just did, right? But let's just look at what we have right here. Theta right here is 40 degrees. And as we know, if we understand a little bit about trigonometry, we'll understand that the opposite side of theta would be right here. So this would literally be the opposite side. And as I said before, is that our radius, this line right here representing our radius, is of 1 unit. So this measures 1 unit. Now, if we were to go by the formula sine theta, right? Using this formula for sine theta, we would actually get the sine of theta, and theta in this case is 40 degrees, is equal to my hypotenuse, sorry, my opposite, which we said is about 0.67, somewhere there, fair enough, 0.67, right, over 1. So we're just using our eyeballs to do that. Now, as we already know that anything over 1, so anything over 1, just want to write it a bit bigger. So we already know that anything over 1, so this is just an estimation, right? Anything over 1 is just itself. So we could have just simply removed the 1 right there and said that the value of sine theta equals 0.67, which is the value on the y-axis. Now, what I would like you to do is just to punch into your calculators the sine of 40 degrees. Just take your calculator. Right, so I'm going to take my calculator and then I'm going to punch in the sine of 40 degrees. Voila. Right, as I said, mine's not necessarily that accurate, but I got 0.6427. Right, so there enough is 0.6 something, as we can actually see it there. Right, So the accuracy in doing that, we literally see that this, I'm just going to write the correct, what's there, right? I'm going to use 6,4 for example. So if you look, for example, that the sine of 40 equals the value of my y-axis. So whatever my y-axis value, that is sine theta, right? So the understanding you should have right here is that y, the value of y, which is my x-axis, which is my y-axis, y is just my y-axis, right? Y equals sine theta, right? So the sine theta actually represents my y-axis, right? It gets interesting as you actually plug in more, you actually try to map this out with more angles. Right? We're going to actually be doing more angles, but let's look further into this. Now, the value of my x-axis, as I said before, is about 0.75 or 6-ish, thereabout, right? So they are very small units, so we know that, give or take 0.5, 0.7, 0.75, 0.76, thereabout, because it looks very much in between, somewhere thereabout, right? So, or we actually have 0.74, that is fine, right? Now, here, this side, our x-axis, if this side is my opposite, this side would have been my hypotenuse. This side would obviously be my adjacent side. Now, looking at my adjacent side, we know that if we were to look at the adjacent and we have the hypotenuse, we could have plugged in the cos theta, which in this case, theta is 40 degrees. And we said that is equal to, and I'm going to put, we said it is actually equal to 0.74 over 1, right? Hypotenuse is 1, right? So what we're saying, therefore, is that if we look carefully now, is that the value of cos theta equals 0.741, right? If we were to, as I said before, is that anything over 1 is, 1 doesn't really change anything. So it answer would be that cos of 40 is about 0.74. Remember that that's also estimated, right? So if I were to punch into my calculator the cos of 40, voila, that gives me 0.766, right? So that's the estimated value, but this is the estimated value, but we got 766. We're just going to work with it, change them out just for accuracy's sake. So if you look carefully, the idea of this is to understand that my x-axis, the value on my x-axis equals the value of cos theta. So cos theta actually equals the x-axis. So therefore, we could actually have a statement to say that when using the unit circle, we could have an understanding that when we look, that if we were to find the coordinates of an angle, the coordinates of an angle, right, the coordinates of an angle on the unit circle actually maps to, so this value would have been cos theta, and this would also be sine theta. So that is how you would actually write, because cos theta represents the x-axis and sine theta represents the y-axis. Alright, so moving along now, so that was just 40 degrees. Maybe that was some mistake, maybe it doesn't really work, but who knows, maybe if we try another one, it probably won't work. So let's actually look at another example. Right, so I'm just going to erase this one. Alright, so look at this example. So we're actually working with 60 degrees, right? So here, this angle is 60 degrees. So theta is 60 degrees. As we already understand, is that our opposite side, or the y-axis, right here, so this would be my y. In this case, the y-axis, right, actually measures, so the height of this axis, or this vertical axis, then is somewhere about right here, right? You can see the lines look fairly enough straight enough to give us a fair approximation of the answer, right? So if we look here, the y-axis is saying about let's say, so y would have been equal to, let's say maybe 0.86 or 87. Let's go with 87, right? So we're going to have it like that. Now the x-axis, which would have been this horizontal line right here, would actually fall right somewhere about here. So this is about 5-ish, right? Maybe 0.49 or just close enough to 5, or it could be 5, somewhere about there. So in this case now, the x value is telling us 0.849, or we could just call it 0.5, right? So that is close enough to the 0.5, right? I also would tell her that if we were to type in the cos of 60, it should give us 0.5, right? But we can see that it's literally close to it. Now, we can actually use our calculators to check our values, right? So our y now, if we want to find the exact value for y, we could actually find the sine of theta. And as I said, sine theta is the sine of 60. So sine theta, so theta is 60, sine theta would have been 0.866, which is literally looking very much accurate even on this diagram here. And we actually got it. So the y-axis equals sine theta again. So we see that again, we mustn't really think that this is a mistake, seeing that we have gotten it twice right on spot, right? So it's definitely no mistake, right? So y equals 0.87. So we can say again that y equals sine theta. Let's look again now where we have theta being 60 degrees. And when we look at it, and the adjacent side is literally pointing close enough to 5 or 5-ish. So in order to get that, we would type in cos theta, which is actually 60. And there we have it, 0.5. So we can say again that it is safe to say that x represents cos theta. It's definitely safe to say it. All right, so one of the other things I just want to point out while I'm doing all of this is that if you can see so far, is that trigonometry is basically an angle-based subject in mathematics. But if you realize that when we're talking about SOH, we generally use SOH for right angle triangles. So if you look carefully, we would actually be spotting our right angle triangle right here. So here would be my right angle triangle. Right, so my right angle triangle comes right here. Right, we could actually look at it here as well, but we're not going to draw that here as well. Right, so that is how the idea right angle triangles actually came into the picture, where we can actually use the principles of right angle triangle to understand or to work with trigonometric concept using SOH. Right? So that's something just to understand, and that's the idea of how right angle triangles came into play. Right? So there's something else that I would like you to notice, is that previously we said that the cost of 40 was 0.766, and we say that sine theta was 0.64. So that's what we had right there. So this one right here, this purple line that you're seeing, is actually cos theta of cos 40 degrees. We saw that you see how wide the x-axis is, or how wide the bottom of this angle actually spans. You'll actually see that the line right here actually becomes the y-axis line right here becomes shorter. Now the more that cos theta decreases, as we see here, where the cos theta, the value of cos theta decreased from 0.766, it actually decreased to about 0.5, right? So that's about 0.166 decrease, right? So the decreased, right, it came right here, and we saw that the value of the y-axis, or sine theta, increases. So you'll actually see a little principle coming out right there. So if you look again, as I'm saying, is that cos theta decreases as sin theta increases. As sin theta decreases, cos theta actually increases. So they affect each other when you look at it like that. So remember now that these actually will measure 1. Right? So that is how the idea of right angles, triangles come about. And sin theta, as I said, represents the y-axis. So we know that this side, which is the opposite side, is very much important to sin theta. And we know the adjacent side definitely is important to it. Right? So that is how the idea of the formula comes in, with that sin theta equals opposite over hypotenuse. Right? Because as we can see in the formula, when the hypotenuse is 1, right, given that the radius using the unit circle, we see that given that this is 1, sin theta would actually equals the y-axis. So the opposite will be the y-axis. I know the y-axis, anything over 1 is just, doesn't change anything. So sin theta gives us the value of the y-axis. So sin theta equals y. The next thing you know is that cos theta, as I said before, equals x, as we have seen it right here. Now the only thing that we have not yet looked at is tan theta. So let's give a look on tan theta shortly. But before looking at tan theta, I just want to do another example so we can see how much this really plays out in our solutions, right? So let us say I'm going to take my protractor again, and this time I'm going to do it on the other side. Alright, so let us look at this next example. So right here I just constructed a 150 degrees angle. So this is 150 degrees, right? So that is a 150 degrees angle. I'm going to actually use this color marker to actually highlight the area that we're talking about. So I hope that actually is clear enough to see, right? So that's just this area right here. If the grid is not there, I also am using the black. Right, so that's the entire area from this point right here all the way back to here is 150 degrees. So theta in this case is 150 degrees. Now when we look at this line, this again now is going to tell us about the coordinates. Let us look at the coordinates of this point right here. So if we were to try and find the coordinates of this point right here, that's where our radius actually connects to the circle. Right, and we say our radius measures 1, right, 1 unit. If we look here for the y-axis, the value of my y-axis is pointing towards 0.5, maybe 0.52 if I'm using this, what is here. So it's just about 0.5. So we use our y-axis would be in the second part of my bracket. So 0.5 thereabout, right? Now if we look here now, is that on the x-axis, right, on the x-axis, we can see that this is about 0.9, like maybe 8.788. So it's just about 0.886. I'm going to use 866, sorry. I'm going to use 0.86.886, just about that. So close enough to 9, you know. All of that, so far as I said before, is just an estimation, right? Because this is not drawn perfectly to scale. So x-axis and then the y-axis, right? So therefore, if cos theta equals the value of my x-axis, it means that the cos of 150 degrees must equal to about 0.86. So we're going to check that. So cos theta, and just to say also that that these values are my negative values. So I forgot to say that just now. So this 0.86 is my negative value. So that's my negative. This is a negative value, right? So it should equal negative 0.86. So, and this now is still going to be positive because the y-axis is right there. So we're going to type in cos of 150 degrees, and we should get negative 0.8 something or 9, something like that. There we go. And here we actually see the negative. So 0.866, right? So we can literally see that that looks very much accurate. So voila. So the cos of 150 degrees definitely equals the value on my x-axis, right? Again, if we were to even write this out, my right angle triangle would actually be reflecting on this side using this sign. Where I'm actually going to look at that shortly so we can actually see something else. So we proved that cos theta equals the value of my x-axis. Now let's talk about sine theta. So sine theta, this value right here, would actually be the opposite side, which would be sine theta. So if you understand that this side, which is the opposite side, whenever I sine the angle, I get the value of my y-axis. So this is why the opposite must always be in the formula of the sine theta, because if you type in sine and type in the adjacent, you're going to get a different answer, right? When we look at the y-axis, which is this vertical side, we get sine theta. We're going to actually punch in that right now. So the sine of 150 degrees, typing that, so it should give us positive 0.5. There we have it, positive 0.5. So that proves to us that the value of my y-axis, which is this side right here, right, which I'm actually going to come here and look at something, because if we're seeing that the 150 degrees is literally to this side, so we would literally be drawing an angle right there, and this no longer is really representing the size of a right angle triangle. But don't mind that, I'm literally about to show you something. Notice I drew my right angle right here, because in drawing my right angle there, it is to understand that right here, this is a straight line. And if this is 150 degrees, it simply means then that this value right here is actually theta right here, actually should equal 30 degrees. Now, if I were to punch in my calculator again, same calculator, right? Just going to clear that, and then I'm going to type in the sine of 30. What is the sine of 30? The same 0.5, because it's literally the same thing. So in reverse then, the sine of 150 degrees points the same value of the sine of 30 degrees, right? So the sine of 30 degrees right here, so theta being 30 degrees right here, would actually give me the same value as theta being 150 degrees. And when we actually draw the line right here, we see that the 30 degrees technically falls on the other side of the y-axis, still pointing to 0.5. If we were to draw 30 degrees here, we would also get 0.5. But the value of the x-axis is now going to land on the positive side. So the value of cos theta is still going to give us 0.86, but it's going to give us a positive answer. Just to type it in so we can see it. So the cos of 30 is going to give us the positive answer, 0.866, right? But it's going to be a positive because 30 on this side now would have been here, right? It's actually reading that the 30 would have fallen somewhere about here, right? So, but if we type in when the angle comes on the left side, remember now that once it comes on the left side, we're now talking about our negative values of x, whereas the values for y are still going to remain positive. So the cos of 150 degrees is going to give you a negative value, whereas the cos of 30 degrees is going to give you a positive value. Now, that's just for that breakdown, but here's something now. Understand now that this side, which is the side where my right angle is, just always understand that this is the opposite side to theta, right? Being the opposite side of the theta, in order to find the value of this side or the length of this side, you must use sine, right? Sine theta, because the y-axis represents sine theta. And once you use sine theta, you must provide the value for the opposite, and you must provide the value of the hypotenuse. Or in the case if you're finding the opposite, then opposite would be x, because you're now going to find, you use sine to find the opposite side if you're trying to find the opposite side, right? Of course, sine and cos can also both be used to find the hypotenuse, because those two are also related. So the idea is that you must have the opposite, or trying to work out the opposite. The opposite must be in your formula then, right? When you're using sine, and the adjacent must be in your formula if you're going to use the cos. So that's key to note, right? We're really going to be going through all of that detail as well, but I'm just saying it. But just to reiterate, if you realize right here that the value of cos again is wide, and if you look carefully that the value of sine again is small, so the x value is larger than the y value, because as theta decreases, right, as theta decreases, well, so theta right here, remember the first one was 40 degrees. If we look here, as theta increases, I should say, as theta increases, reading it from this side, as theta increases, the value of cos actually is going to, so as theta increases, the value of cos is literally going to decrease. So here cos was 40, and then as soon as the 40 increase, so as theta increase to 60 degrees, remember this, what the green line, it was 60 degrees, this angle. We saw that cos also decrease and sine increase. So when it was 40 degrees, cos was more and sine was less. But when the theta decrease, when theta increase, right? When theta increase, cos decrease and sine increase. Here again, we saw where theta, which one is actually 150 degrees, we saw that when theta increased to 150 degrees, the value of cos, though it's actually longer here, looking at it from this side, but this side is really the 30 degrees angle right here. But the right here is the 150 falls, the radius of the 150 falls here, which is pointing to a negative value. We know that 0.5 is still bigger than negative 0.866. So you can see that cos really decrease as sine still remains at a higher numerical value, right? But technically it's still wider. But you get the idea, I'm sure of it, right? So if we were to read it as 30 degrees, 30 degrees would have given somewhere about here. So after 30 degrees comes 40 degrees. We saw that cos is decreasing as theta is increasing. And then we go into 60 degrees, cos also decrease again. We saw that sine, however, we saw that if it was 30 degrees would have been right here, and we saw that sine would have been about right here. So sine would have been smaller in this case, being sine 30. And then we saw that as sine increases, right, the value of sine also increase from 0.5 to 0.76, right? And then as theta also increase again, we also saw that the value of sine also increases. So those are just basic things to understand about your unit circle. Now there's one last thing that, as I said before, that I didn't touch, and that we still haven't mentioned anything about tan theta, right? So I'm just going to erase this. So tan theta now is that, as we know, that tan is really the shortening for tangent. And if I was supposed to use any one of these, I'm just going to use the first one that we did right here, where we actually did. So remember that this was literally, so remember that this right here, this angle right here was actually, this angle was 40 degrees, the purple mark right here, right? So I'm just going to draw a line perfectly on the, remember that tangent touches a point on the circumference. So it just perfectly touched the point on the circumference, right? So drawing my tangent right there. So in drawing this, this actually would represent tan theta. The size of this line represents tan theta, right? So that is the tangent right there. So this represents tan theta, and as we see here is that tan theta equals opposite over the adjacent. So in other words, if you want to find the length or the size of this line, then we simply find the tan of the 40 degrees. Remember that this dot right here, this dot right here actually is 40 degrees. That's theta. And remember the coordinates of this line is the x-axis is 0.766 and the y-axis was 0.642. Now, if I was supposed to take my calculator, right, and just simply divide the opposite, which this case, the y-axis is my opposite, so that's 0. So this is my opposite. So remember, this would have been the opposite, OPP, right? So that would be 0.642, which is the value of my y-axis. And we are saying that opposite divided by the adjacent. The adjacent would have been the x-axis, which is going to be 0.766, 0.766. When I divide it, I'm actually going to get 0.838, right? So just remember that value, just look at it, right? So that's 0.838 or 0.884 then. So 0.84. Now just remember that value, and what I'm going to do is that I'm going to type in the tan theta, and theta in this case, as I said before, is 40 degrees. Because this tangent is coming from this point where theta was 40 degrees. If I had put it up here, theta would have been much longer, right? And we would have to find the theta of 60 degrees because this green line represents 60. But here tan is 40, and here we go, we actually got by the same answer. The reason why there's a little change in the decimals is because we rounded off the figures. But if you were to just go ahead and go back and type in what sine of 40 divided by the cos of 40, we will get back the 0.8390 as we just got it. See that? Just remember that. And look again, tan of 40. So that tells us the size of this line right here. Right, so that's really it in a nutshell. Right? One other thing that you'll notice is that y squared plus x squared equals 1. Right? There's a little thing, if you actually look at this, it looks very similar to the Pythagoras theory. Because it technically falls in line with the same thing. Right? If I were to square the value of my y and add it, right, and add it to the value of my x, I would get the value of the longus of the radius, which in this case would have been the hypotenuse. So this would be the hypotenuse, right? And we know the hypotenuse would have been the longest side. So let's look at that. So again, we're going to use this one, right, because we have the coordinates right here, right? So we have, if we were to find the value, so this right here is cos of 40. So if we were to take the cos of 40, so just going to write it. So the cos of 40, and we're going to find it, and then we're going to square it. Right? So that's what we have. Then when we press the plus button, so we're going to add it to the value of sine 40. So the value of sine 40, and whatever I get there, I'm going to square it. So that's my answer, 1. There you have it. So we actually get back the longest side. If I was to use another number, let's say we have these coordinates. We have these coordinates. I'm not going to use a negative in this case. I'm going to use a positive because we saw that cos theta is also the cost of 30 would have given us a positive answer. So I'm not going to use the negative in this case, right? So we're going to use the cost of 30. So so they start with the y, so the sine of 30, right, equals, and then we square it, right? And then now we actually going to add that, so we're going to add it to the cos of 30, and the answer we get there, hold on, we're going to add it and put that in bracket, cos of 30, and then close bracket, and then I square it. So we should get back 1. Voila, 1. So we actually see that this actually proves Pythagoras' theory. We know that this one right here, we could have written as equals 1 squared, right? Because 1 squared is just simply 1, right? So if you even look at it like that, you know, it probably makes it even more clearer, right? But this is really the unit circle, and this is how we actually arrive by the right angle concept in trigonometry, and this is how we actually arrive by the tan theta and cosine theta and our sine theta. Okay, so that takes us to the end of this lesson on trigonometry, where we use the unit circle to understand core foundation of trigonometry and how SOH actually came about. Now in my next video, I'll be showing you when and how we use trig functions to actually solve right angle triangles. So please remember to like, share, and subscribe to my channel, and stay tuned for the latest updates. Thank you.